Good morning, folks. So last time we talked about the comparison test, the limit comparison test, and the direct comparison test. Today, I want to talk to you about alternating series. So let me get my screen share going. Oh, there it is. All right. I think I'm going to switch pens. This pen's been giving me a hard time. Specifically, so the convergence tests which we still need to learn are alternating series, and this is section 11.5, and then the root and ratio test, which is section 11.6. I see Naz has some homework questions you wanted to look at. I'm okay with starting off with a couple of those. So before we dig into the new stuff, let's look at one or two problems from your homework. Okay. 7 is pretty straightforward. There's more than one way to attack this, but that's a fine one to start with. So first we'll do some practice problems. Just like with a lot of integrals, there is more than one way to solve the problem. Some things you could do by parts, but you could also do trig sub or something like that. With these series, often there's more than one approach that would work. I could use the limit comparison test here. But the limit comparison test is a little bit more complicated and a little bit more demanding than the direct comparison test. So if I can, I would like to use that. First, observe that TFD is inconclusive. You should always run TFD first. Usually I do it in my head. Here, the limit as n goes to infinity of the ANs is the limit as n goes to infinity of 9 over the square root of n squared plus 9. And notice I'm not saying that this is equal to this series. Please never do that shit. I see it a lot, way more than I should. I'm running a test called TFD, and I should always let my reader know. So when you solve your problems on the test or in your homework, you should be doing the same thing I'm doing. Don't say that this is equal to this. It's not. They have nothing to do with each other, besides being connected through TFD. So I let my reader know what I'm doing. I'm running the test for divergence, which says, calculate this limit. If that limit's not 0, the series diverges. Well, here the limit is 0. because as n goes to infinity, I get 9 over the square root of n squared goes to infinity plus 9. That's 9, oops, sorry. That's equal to 9 over the square root of infinity, which is 9 over infinity, which is 0. So this is inconclusive. I might consider the integral test, because it's true that f of x equals 9 over a square root of x squared plus 9 is decreasing, continuous, positive. But it's a lot of work, and the related integral requires trig sub. It would take a while. Let's not do that. So the integral test is kind of a last resort. The direct comparison test, though, this will work nicely. Observe that the square root of n squared plus 9 is definitely greater than or equal to the square root of n squared. Oh wait, actually, this might be trouble. Yeah, I made a claim that DCT will work nicely. I might have to walk that back. If I take reciprocals on both sides, 1 over the square root of n squared plus 9 is thus less than or equal to 1 over the square root of n squared. So 0 is less than or equal to, because this is positive, 9 over the square root of n squared plus 9 is less than or equal to 9 over the square root of n squared. But this guy is the same as 9 over n. So while this inequality is definitely true, it's not useful. Why is this not useful? So why is this, while true, not useful? Yeah, because if I sum the thing on the right, because sigma 9 over n summed from 1 to infinity is equal to 9 times sigma n from 1 to infinity, 1 over n is a divergent series. Right, this piece is a divergent p series. P is equal to 1, which is not bigger than 1. So I would be showing with DCT that my guy is a little bit smaller than something which, when summed, is divergent. And being smaller than a divergent series doesn't prove anything. Every convergent series is smaller than a divergent series. So are a bunch of divergent series. So it's not helpful. I don't learn anything. This is actually inconclusive also. Inconclusive based on this inequality. Now, you might ask, does that just mean I built a shitty inequality? Could I have found a better inequality that would have been useful? Maybe, maybe. But the obvious inequality starts with the obvious observation that adding 9 makes this thing bigger, so it makes the reciprocal smaller. It's the natural thing to want to compare to. But my guy is, turns out, a little bit smaller than a divergent guy. And that means things could go either way. So it's inconclusive. So this is really a good problem for limit comparison tests. So I'll just copy the series down again here. And based on what we just did, I have a sneaking suspicion that this is a divergent series, because it only differs from a tiny little bit from the divergent series that that we just looked at, the 1 over n series. So here I'm going to run the limit comparison test, and what we just did tells me how to pick my Bn. If I just pay attention to the important shit here, so An is 9 over the square root of n squared plus 9. If I ignore the 9 downstairs here, because he really doesn't contribute too much, then I get 9 over n. So this thing behaves an awful lot like 9 over n. So I'm going to pick Bn equal to 9 over n. One over n would also be a reasonable choice. Then I calculate C. C is the limit as n goes to infinity of An over Bn. And again, I want to comment on the notation. I'm telling my reader what test I'm using. I'm telling them that I chose Bn to be 9 over n, and then I'm telling them what I'm calculating before I actually do the calculation. All of this may feel superfluous, but it's not, because if someone's reading your work, they need to see this shit in order to know what the fuck you're doing. So please don't skip writing this. Also, on the test, if you write this, but then you mess up the algebra or the calculation, I can at least give you partial credit for knowing what the limit comparison test asks you to calculate. So it's got advantages in more than one way. All right, this limit is the limit as n goes to infinity of 9 over the square root of n squared plus 9, all divided by 9 over n. I can flip and multiply. The 9's cancel. And I get n over the square root of n squared plus 9. Then I divide top and bottom by n. Right, because if you try to plug in infinity, this looks like infinity over infinity. You could use L'Hopital's rule if you wanted to, but L'Hopital's rule is a mess here because the derivative of the square root is unpleasant. So you should use the renormalization trick wherever possible. Don't use L'Hopital's rule unless you absolutely must. Dividing top and bottom by n, I get 1 over the square root of n squared plus 9 times 1 over n, like this. Yeah, L'Hopital's rule is a mess here. I don't recommend it. You could probably make it work, but it's going to be a mess. Then I treat the 1 over n downstairs here as the square root of 1 over n squared. So I get limit n to infinity, 1 over the square root of n squared plus 9 times the square root of 1 over n squared. 1 over n is the same thing as the square root of 1 over n squared, as long as n is positive. And here n is going to plus infinity, so I'm definitely only considering positive values of n. This is the same as the limit as n goes to infinity of 1 over the square root of n squared plus 9 times 1 over n squared. That's 1 plus 9 over n squared. Yes. Well, TFD, remember we did TFD at first. TFD is inconclusive for this series. So yeah, a couple people wanted to come back and look at these first few things. So let's look at these again. We already ran TFD. We didn't need the renormalization trick for that because the top is constant. Here, the limit from TFD is 0, so that's inconclusive. So we've already done TFD. No need for any more TFD. And then Nick, did you get what you needed from this page? I can hang out here just a second longer. All right, moving on. So we've determined that TFD doesn't work, integral test might work, but it sucks. DCT hard, at least. The obvious DCT doesn't seem to work. So we do LCT. I picked Bn to be 9 over n because I realized that this thing is actually very similar to 9 over n. If you cover up the 9 downstairs, he becomes 9 over n. No, definitely not, Morgan. So one of the last things we're going to talk about before the test is how to decide which method to use. There definitely is not time to run through every single method on every single problem. So you want to, just like with the integration, you want to develop a sense of what method to use for what problems. And you do not want to burn time going through every single one. I'm doing that way now to try and give you guys a feel to help you develop that intuition. But the place we want to get to is a place where you can smell which test to use ahead of time. So now as n goes to infinity, 9 over n squared goes to 0. So this is 1 over the square root of 1 plus 0, which is 1 over root 1, which is 1. Therefore, what does limit comparison test say? Can I conclude that my series converges? Can I conclude that my series diverges? Can I do any of that right now, or is there something else that I conclude? Good. The series I was given does the same thing as the series of the BNs. Therefore, our series converges or diverges together with sigma n from 1 to infinity 9 over n. What's more, sigma n from 1 to infinity 9 over n is 9 times sigma n from 1 to infinity 1 over n is a constant multiple of a divergent p-series, because p is equal to 1, which is not, which is not greater than 1. Therefore, sigma n equals 1 to infinity 9 over n diverges, and by LCT, our series diverges as well. Sigma n equals 1 to infinity 9 over square root n squared plus 9 diverges also. Okay, so that's how this works. Is it ever appropriate to say it's the harmonic series which is known to diverge? Yeah, so Thomas asked a question in chat. Would it be okay to say sigma 1 over n is the harmonic series which is known to diverge? Sure, that's fine, and it's a little bit faster. I have no problem with that. Just make sure that your logic is not circular. Make sure that everything is reasonable, makes sense, and follows from what came before. Yes, Fernando, even if C is irrational, so remember the requirements, let's say it like this. So C is positive and finite. That's all I require. So being irrational, if C came out to the square root of 2 or pi, that's still fine. As long as C is positive and finite, then the series will converge or diverge together. There were a couple other problems that were requested here. I would like to take a look at number 10. 12 was requested, 15. Mariano, yeah, if P is greater than 1, then a P series will converge. So it only holds for P series, only series of the form 1 over n to the P, so like 1 over n squared, 1 over n cubed. If you have 1 over n to some power being summed, then that series will converge if and only if P is greater than 1. All right, let's look at number 10. here we have sigma n from 1 to infinity, 1 plus 1 over n squared times e to the negative 3n. This one will fall to DCT. He passes TFD. If you send n to infinity, this piece goes to 1, and this piece goes to 0. 1 times 0 is 0. So I'll write it down just this one more time. Lim n to infinity of the ANs is lim n to infinity 1 plus 1 over n all squared e to the negative 3n is equal to 1 plus 0 times 0, which is 0. E to the negative 3n goes to 0 because it's an exponential function that's decaying, right? So if you don't remember those rules, e to the negative infinity is 0. Again, go back to section 11.2 or even section 2.6 and remind yourself how those limits work. So this is inconclusive. But DCT will work here. Observe that 1 plus 1 over n squared is definitely greater than or equal to 1. Right? Because I'm taking 1, I'm adding something positive, and then squaring. This implies that 1 over, oh wait, no, how do I say this? What do I want? I want, so this implies, oh, fuck me, is this not gonna work? This might not work. God damn it. All right, so this implies that 1 plus 1 over n squared e to the negative 3n, I may have to take that back again, is bigger than e to the negative 3n. Yeah, because I'm not going to be taking reciprocals here. DCT is also not going to work. So the sum sigma e to the negative 3n is convergent, but bigger than convergent could go either way. Yeah, so I have to walk that back again. The inequality here points the wrong way for DCT also. So this is also not useful. My series, the terms of my series are a little bit bigger than the terms of this guy. This guy is convergent. He's a geometric series. I could go into those details if we wanted to, but I don't want to here because it's not useful. So this is going to be another LCT. And I'm not even considering integral test here. I do not want to integrate that thing. So here, AN is 1 plus 1 over n squared e to the negative 3n. Since this piece goes to 1, the natural thing to compare against is this guy. So I'm going to pick Bn to be e to the negative 3n. The limit as n goes to infinity of an over bn is the limit as n goes to infinity of 1 plus 1 over n all squared e to the negative 3n over e to the negative 3n. Those cancel, and you get limit n to infinity 1 plus 1 over n squared, which is 1 plus 0 squared, which is 1. And this is the number C. Since C is positive and finite, sigma an and sigma bn converge or diverge together. Moreover, sigma Bn is the sum from 1 to infinity e to the negative 3n, which is the sum from 1 to infinity e to the negative 3 all to the n. So here I'm using a rule for exponents that says a to the b all to the c is a to the b times c. So e to the negative 3 times n is the same as e to the negative 3 all to the power of n. This is a geometric series with common ratio r equal to e to the negative 3. So the absolute value of r is the absolute value of e to the negative 3 is e to the negative 3, which is 1 over e cubed, which is smaller than 1. So sigma Bn converges. Thus, by LCT, sigma An, which is our series, sigma n from 1 to infinity, 1 plus 1 over n all squared e to the negative 3n must also converge. All right, so there it is. I thought DCT would work for this. It doesn't, but LCT works great here. We chose Bn to be e to the negative 3n because I knew that this piece of the an's didn't really make a whole lot of a difference, because as n gets bigger and bigger, this part goes to 1. So really the essential behavior of my series is coming from this piece, because this piece right here goes to 1. So I picked my Bn to be that essential part. Calculate my limit of an over Bn, that comes out to 1. Since 1 is positive and finite, the two series got to do the same thing, converge or diverge together. And the series sigma Bn is a convergent geometric series. The idea for the choice of Bn, what you want to do is look for what I call the essential behavior in An. So I ask, what piece of this thing really determines how it behaves? Is it this guy? Is it this guy? Since this piece goes to 1 as n goes to infinity, he doesn't really have an effect on the convergence or divergence of the series. So we're not looking for something that's necessarily larger or necessarily smaller for LCT. What we're trying to do is isolate the important shit. So remember when you were finding horizontal asymptotes in Calc 1, or when we were looking at limits of sequences back in section 11.1, you had to sort of identify what piece is growing fastest, or what piece is the most important for that sequence, or for that function. Here, this is the important piece, because this piece doesn't really contribute much. If you multiply something by a number that's very, very, very close to 1, then you're not really changing it. Since this piece is usually very, very, very close to 1, he doesn't really change the overall size of An. This piece, on the other hand, goes to 0 very quickly. So this is the important part of An, and that's how I knew to pick him as Bn. So to pick your Bn, you ask, what piece of An really determines the behavior? If there's something weird and annoying in there, you try throwing that thing away, as long as that thing doesn't grow or decay very, very fast. This does neither grow nor decay very, very fast. It goes to 1, and it goes to 1 somewhat slowly. But this piece goes to 0, and it goes there very, very quickly. So this is the important piece. That's why I picked him to be Bn. Okay, so that's number 10. I think there's 1 or 2 other really good problems in here. 11, DCT will work. This is bigger than 1 over n. 12, DCT will work. 13, 14, 15 somebody asked about. DCT will also work here. So I'll let you guys pick. I'm going to do one more. Do we want 11, 12, or 15? 15? Okay, 15 seems to be the popular one there. Morgan asks, in LCT, it says that AN and BN have to have positive terms. It means that you can't have any negatives. AN has to always be positive. BN has to always be positive. So most of the series we've looked at so far have only positive terms. But some series, like some geometric series we've looked at, have both positive and negative terms. So it just means that the fact that AN and sigma BN have to have positive terms only means that AN and BN themselves must always be positive. You guys chose 15. So let's look at 15. I think 15 is probably the easier of them, but we want to investigate the convergence of the series sigma n from 1 to infinity arctan 5n over n raised to the 1.2. Let's see now. I think I could do this with limit comparison or with direct comparison. First, let's run TFD. The limit as n goes to infinity of arctan 5n over n to the 1.2. The top here, arctan of 5n, is going to arctan of infinity. And the bottom is also clearly going to infinity. Arctan of infinity is pi over 2. Pi over 2 divided by infinity, something finite divided by infinity, is 0. This is inconclusive. But it does give me a little hint as to how I might get away with a direct comparison. Remember, arctan is an increasing function. I won't do that. So arctan of 5n is always less than or equal to pi over 2. Arctan of anything is always less than pi over 2. And as long as n is positive, arctan of n is positive. So for all n greater than or equal to 0. This implies that 0 is less than or equal to arctan 5n over n to the 1.2 is less than or equal to pi over 2 divided by n to the 1.2. I'll call this inequality star. Also, sigma n from 1 to infinity, pi over 2 divided by n to the 1.2 is equal to pi over 2 times sigma n from 1 to infinity, 1 over n to the 1.2. And this is a p-series with p equal to 1.2, which is bigger than 1. So my series is term for term smaller than sigma then pi over 2 sigma 1 over n to the 1.2, which is a constant multiple of a convergent p-series. Therefore, my series sigma n from 1 to infinity arctan 5n over n to the 1.2 must also converge. If I had to guess, I'd say the thing that makes this problem intimidating, or the reason it was requested by so many folks, is the arctan. We got to get over this fear of the inverse tangent function. Inverse tangent function is actually your best friend. It's a great function. It's so nice. It doesn't do anything bad. It's monotone. It's odd. It's got beautiful symmetry. It's easy to work with. It really is. Just remember the graph, right? Got to know the graph of arctan. If you know the graph of arctan, this shit's easy. If you don't know the graph of arctan, this shit's hugely intimidating. Right? This is arctan. He's a monotone increasing function that goes towards pi over 2 on the right and negative pi over 2 on the left. This is the graph of arctan x. So arctan of anything is always bounded above by pi over 2, which means arctan of 5n over n to the 1.2 is bounded above by pi over 2 over n to the 1.2. And if you sum these guys, you get a constant multiple of a convergent p-series. So my series is term for term smaller than this guy, which is a constant multiple of a convergent p-series, so he's convergent. Therefore, my series must also converge. Not bad, not bad at all. But you gotta be comfy with arctan. So please get comfy with arctan, right? You notice he showed up on exam 1, he showed up in a bunch of problems in the homework before that, and then exam 1 had one problem that was straight up just an integral of the inverse tangent function. Here you've got more arctans showing up in the homework. You have reason to suspect that the inverse tangent function will be relevant throughout the rest of this course. And it is, not just here, but later as well. All right. The rest of these are things that we have pretty much played with. I don't think there's anything here that you should be too afraid of. So I'm not going to spend more time on homework problems. Number 12, I'll give you a little hint here. Try a direct comparison. 1 over n factorial. N factorial is fucking huge. So you can compare against something like 1 over n squared or 1 over n cubed or 1 over n to the 4. This will be smaller than all of those because n factorial is way bigger than n squared, n cubed, n to the 4. Another hint I'll give, 14, try a limit comparison here. This little piece up here, the 1 over nth power goes to 0. So this is a lot like 10 over n to the 1. All right. I think that's enough homework. So I'm going to go ahead and introduce the new material for today, which is on 11.5. Alternating series. So far, all of the series we've looked at, except for some geometric series. No, we cannot find the sum here. So that problem does not ask you to find the sum, and we can't. Finding the value of the sum here is very hard. Finding the value of the sum here is even harder. So all we want to do is answer whether it converges or diverges. Okay, so 11.5, alternating series. The integral test, the test, the direct comparison test, and the limit comparison test all have this requirement that your series be positive, contain only positive terms. they each say it in different ways. The integral test says f of x, the function that you interpolate, has to be positive, continuous, and decreasing, which means your ANs have to be positive. The direct comparison test says 0 has to be less than AN, has to be less than BN, so AN and BN both have to be positive. And the limit comparison test has the statement sigma AN and sigma BN have to be series of positive terms. They all require that all the terms be positive. Not all of our series are like that, though. Many of our series are not all positive terms. And the alternating series test is the first thing we have to deal with those besides geometric and telescoping techniques. What's cool about 11.5 is not only do we get a new convergence test, but we also get a tool for estimating the value of the series. So first, a definition. A series in which every other term changes sign is called an alternating series. So it alternates from being positive and negative. We usually write these as sigma n from 0 to infinity, -1 to the n bn. So that would be like b0 minus b1 plus b2 minus b3 plus b4 minus b5 and so on. Or sigma n from 1 to infinity, -1 to the n bn, which would be like minus b1 plus b2 minus b3 plus b4 minus b5 plus, and so on. So these are the sort of normal notations, and here the bn's are understood to be positive. So that these terms are actually changing sign. But there's other ways to write them also. So this notation is kind of what you'll see most of the time, but it's not the only way. The thing to remember is that a series where every other term changes sign, that's an alternating series. So if it goes plus, minus, plus, minus, plus, minus, that's an alternating series. An example. Sigma n from 1 to infinity, -1 to the n plus 1 over n. This is an alternating series. Because if you write down the first few terms, when n is 1, you get -1 squared over 1 plus -1 cubed over 2 plus -1 to the 4 over 3 plus -1 to the 5 over 4 plus -1 to the 6 over 5 and so on, which is the same as 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5. So we're changing sign. So this is an alternating series. In fact, this guy has a name. This one is called the alternating harmonic series. Because it's the harmonic series, but it alternates, right? And I hope you see what I mean by saying like this is the standard notation, but it doesn't always look like that. The power of -1 here is an n, it's n plus 1, but it still does the same thing. Still makes you flip from plus, minus, plus, minus, plus. Another example. This guy, believe it or not, is an alternating series. I'll show you why. That's the sum from 2 to infinity cos n pi over the natural log of n. That's cos 2 pi over log 2 plus cos 3 pi over log 3 plus cos 4 pi over log 4 and so on. But what is the cos of 2 pi? Cos of 2 pi is 1. So this is 1 over natural log 2. The cos of 3 pi is negative 1. So this is minus 1 over ln 3. Cos of 4 pi is plus 1. And so on. So again, the series changes sign every other term. Plus, minus, plus, minus, plus. So cos n pi, a neat observation. For integers n, the cosine of n pi is actually the same as negative 1 to the n. Any questions about what an alternating series is? Or how to recognize them? I've said it a few times. It's always a good idea to write out the first few terms of your series, especially if you don't know what else to do, or if you're not sure, or if you just want to get to know the series a little bit better. Sometimes the sigma notation can hide behaviors. So it's never a bad idea to write out the first 1, 2, 3, 4, 5 terms of your series. Especially like here, it's not at all obvious that this is going to be an alternating series unless you happen to know this fact ahead of time. But after you write out the first few terms, you see, oh, plus, minus, plus, minus. It is an alternating series. So an alternating series is a series where every other term changes sign. And usually we write the positive part of the summand as Bn. So here I would say Bn is 1 over n. Here I would say Bn is 1 over the natural log of n. The Bn is the non-alternating part. If you notice that the terms of the series are flipping sign, then it is an alternating series. So if you notice that every other term changes sign, then your series is alternating. If it doesn't change sign exactly according to that pattern, right? Every other term is changing sign. Like if it was plus, plus, minus, minus, plus, plus, minus, minus, that's not an alternating series. But if it does change sign every term, either plus, minus, or minus, plus, then that is an alternating series. But it has to be exactly that pattern. Every other term has to change sign. The new convergence test here is called the alternating series test. We're not very clever when we name things. And the good news is this is one of the easier tests to use. So this says if sigma n from wherever to infinity, negative 1 to the n bn, or whatever, is an alternating series, And you need two things. The sequence Bn is decreasing, and the limit of the Bn's is equal to 0, then the series converges. Yeah, everybody likes easy. Now the series doesn't have to look exactly like this, right? It could be any alternating series. But if you have any alternating series where the non-alternating piece of the sum ends is decreasing with limit 0, then the series converges. That's it. But there's more. There's an estimation theorem for alternating series. And this is some good shit, because it's the first tool that we have for summing series and actually getting an idea for what the series converges to. It says if S is a convergent alternating series with positive or non-alternating parts Bn and capital Nth partial sum Sn, then the full value of the series minus the nth partial sum in absolute value is less than or equal to B sub capital N plus 1. So S here, this is the sum of the series. The sum, or you can call it the value. Sn is the nth partial sum. And that difference there, this is called the error in the nth partial sum. So in other words, the nth partial sum differs from the full value of the series by no more than the positive part of the next term. So this allows us to not only, so Sn is a good way to approximate S. If you plug in a big number for capital N, then Sn should be pretty close to S. This tells us exactly how far off it could be. So if I want to know, what does my series converge to? I say, all right, well, I'm going to take a large partial sum. I'm going to take like the 10th or 15th partial sum. That should be a pretty good approximation. But how good? Can I be quantitative about the error? And this theorem says, yes, you can. The error in the nth partial sum, which is this thing, is no larger than the next term. The proof here is not too bad. And I'm going to prove both of these things at once. I'm going to prove that the alternating series test works and that this estimation theorem works. It's nice because it's just a picture. Suppose the first term of my series is over here, so B0. That's also equal to S0, the very first partial sum. B1 is going to drag me to the left. Because I have to move to the left when I subtract B1. So I start out here at B0. S1 is B0 minus B1. And then because the series alternates, the next term has to be negative. And the term after that has to be both positive and smaller than B1. Because one of my hypotheses is that the sequence Bn is decreasing. So B1 is not as large as B0. Maybe 0 is over here. So first we go from 0 all the way out to B0. We add B0. Then B1 takes me back the other direction, but not as far. So I start here at 0. B0 takes me to the right. B1 takes me back to the left, but not as far as B1 because Bn is decreasing. Then B2 is going to take me back to the right, but not as far as B1 because the Bn's are decreasing. So here's S2. Can you see what's going to happen? B3 will take me back to the left, but not as far. So I land here at S3. And then this continues. B4 will take me back to the right again, but not as far. And I land here at S4. So my sequence S0, S1, S2, S3, S4 is nesting. And since the BNs go to 0, the distance that I jump back and forth eventually goes to 0, which means not only are these guys coming in like this, but that they have to eventually land somewhere, and that's the value of the series. So if you have an alternating series where the BNs are decreasing and have limit 0, this nesting has to lead to some fixed number in the middle. That number is the sum of the series. What's more, if you look at the distance from S to any of its particular partial sums, the distance from S to, let's say, S2, so here's the distance from S to S2, that has to be smaller than B3. Because of this nesting, right? So let's look, the distance from S to S0 is this distance. And then the size of B1 is this. I know B1 jumps me from S0 all the way over here to S1, so it had to jump over S. So the distance from S0 to S has to be less than B1. The distance from S to S2 has to be less than B3. The distance from S to S3 must be less than or equal to B4. The distance from S to S4 must be less than or equal to B5, and so on. In general, the distance from S to Sn is less than or equal to Bn plus 1. Because to go from Sn to Sn plus 1, we're going to walk over Bn plus 1, but that means jumping all the way over S. So the distance from S0 to S has to be smaller than B1 because when I go from S0 to S1, I'm moving left by B1 and that jumps me over S. So this distance has to be smaller than this distance because this distance is contained within this distance. Then this distance to this distance has to be smaller than this distance because this is contained within this. What is this? Well, that's B2. So the distance from S1 to S is smaller than the distance B2. The distance from S2 to S has to be smaller than B3 because B3 is this distance and this is contained within this. So this has to be smaller than this. And there's nothing special about 0, 1, 2, 3. This always works because you're always jumping over S in the middle to go from Sn to Sn plus 1. And going from Sn to Sn plus 1 means moving a distance of Bn plus 1. That's it. That's the proof. I think there are probably animated versions of this. So I'll give just a second here, and then I'll look at an animated version of this to try and help you see it. The book also has this picture. So maybe first I'll show you the book. Here it is. Here's the distance B1, jumping you from 0 to S1. And then B2 is subtracted, jumps you back. So the distance from here to here is smaller than the distance from here to here. And that distance is B2. Then the distance from here to here has to be smaller than the distance from here to here, but that's B3. So in general, where is it? In general, it's here somewhere. There it is. In general, the distance from S to Sn is always less than Bn plus 1. And the book is doing this shitty thing where they use the same letter, lowercase n, for the partial sum as they use for the index. I don't like that. I'll never do that. But that's the important thing, right? So I'm going to come back to the dot cam again for a second. You guys can make sure you've got this theorem, both the alternating series test and the estimation theorem written down in your notes. So the alternating series test says if you have an alternating series where the bn's are decreasing and have limit 0, then that series converges. And the estimation theorem says that the nth partial sum is off from the full value by no more than the next term of the series. I'm going to look for that animation. There should be a nice GIF. I don't see it here yet. What's this? Does this work? No, fuck that. Come on, Google. Wow. Wow, really? All right, I'm a little disappointed. Well, maybe not. Maybe I'll have to make one. If I don't see one here in the next few seconds, I'll give up. Series. Let's see, power series. Program equals infinite series. Some of these look pretty cool, especially for people into fractals, but I don't see what we're looking for here. Nah, this all kind of sucks too. All right, I'll see if I can make one for you guys. But the picture is there, right? The picture is exactly this. The nth partial sum, the distance between the full sum and the nth partial sum is the distance from S to whichever partial sum you want, S2, S3, whatever. That distance, like for example, the distance here from S to S1 is smaller than B2 because B2, or sorry, what is it? B2 jumps you back over S to S2. So that's the result. I usually use TIKZ, T-I-K-Z, which is a package for the markup language LaTeX when I need to make an image for mathematical stuff. But I want to start using the stuff that 3 Blue 1 Brown uses, which is called PyMath. It's a Python library for mathematical animations together with TIKZ. If I do take the time to do this, I'll post the code. The internet has indeed failed us, Lucas, I agree. So how do we use this shit? Let's investigate the convergence of the alternating series that we looked at the start. Sum from 1 to infinity, -1 to the n plus 1 over n, and approximate it the value, because I know ahead of time that this converges, correct, with error less than 0.0005. So I should get at least the first 2 decimals correct and hopefully the 3rd decimal place correct as well. Python's easy. Yeah, you should learn Python. There's a good website for it. There's 2 easy ones actually. Animating the boring stuff using Python. And what was the other one I was using? Sorry, not animating, automating. So this website is really good. Automate the boring stuff with Python. And then the other one that was useful for me, I'll post it to Canvas if I remember it. I can't remember it right now. Okay, so for reasons that I will be able to explain to you after we talk about power series, I actually know the exact value of this series. The exact value of this series is the natural log of 2. And I'll show you why later. But for now, I'm going to run AST, then I'm going to use the estimation theorem to try and get this, and then I'll show you with Wolfram alpha that it is indeed within the bound. So first, AST, alternating series test. Here, the BNs are just 1 over n. Since n is increasing, Bn equal 1 over n is decreasing. Also, the limit as n goes to infinity of Bn is the limit as n goes to infinity of 1 over n is 0. Thus, by AST, the series converges. To estimate S with error less than 0.0005, we will use Sn. But for what value of capital N? right? So do I use S1, S2, S3, S4? How far do I need to go in this series before the partial sum will have error less than that? By the estimation theorem, the full value of the series minus the nth partial sum has absolute value less than b sub cap n plus 1. I want to make this, I want to make s minus sn, sorry for the bad handwriting, I want to make s minus sn less than 0.0005. So it suffices, since s minus sn is smaller than bn plus 1, or less than or equal to bn plus 1, if I want to make that less than 0.0005, I just have to make this less than 0.0005. So it suffices to solve bn plus 1 is less than 0.0005. Since Timmy is shorter than Joe, if Joe is shorter than Sally, I will know that Timmy is shorter than Sally, right? It's the transitive property. Bn plus 1 is 1 over cap n plus 1, because Bn is 1 over n. So I need to solve 1 over cap n plus 1 is less than 0.0005. Sometimes these inequalities are easy to solve by hand. Sometimes they're very hard to solve by hand. This one is not bad. I'm going to do it by writing the right-hand side as a fraction. That's 1 over n plus 1 is less than, this is 5 over 10,000. Right, 0.0005 is 5 10,000ths, or 5 times 1 over 10,000, or 5 over 10,000. Just rewriting this decimal as a fraction. I can cancel the 5s. 10,000 divided by 5 is 2,000. Yeah, sure. So I'll leave it like this for as long as I can. So my right-hand side, I can simplify. This is the same as saying 1 over n plus 1 is less than 1 over 2,000, because 10,000 divided by 5 is 2,000, which is the same as saying, if I take reciprocals on both sides, the inequality flips over. N plus 1 is greater than 2,000. Which is the same as saying, and I'm only writing it in this weird horizontal way so I can leave this stuff up here, which is the same as saying n is greater than 1999. So S 1999 is very, very close to the full value of the infinite series. I gotta bump this up now, I'm sorry. And the error is guaranteed smaller than 0.0005. So S 1999, that's the sum from n equals 1 to 1999, negative 1 to the n over n. Sorry, negative 1 to the n plus 1 over n. Now, I don't want to calculate this by hand, that would be horrible, right? This is 1 minus 1/2 plus 1/3 minus 1/4 plus all the way out to plus 1 over 1999. And that would take me a long time to figure out by hand, so I'm going to go ahead and scoot to Wolfram alpha. And I'm going to ask it to calculate the sum of -1 to the n plus 1 over n from n equals 1 to n equals 1999. And I'll find that this is exactly this horrendous, terrible fraction, which has decimal representation 0.6933972, and so on. What is the actual value of the sum? Well, I claim that that's the natural log of 2. And S is equal to the natural log of 2, which is 0.693147, blah, blah, blah. So here we are. Like I said, I can't explain to you right now why the full series sums to the natural log of 2. We need to talk a little bit about power series for that. But what we were hoping, we said we want our error to be less than 0.005. We solved the inequality to find which partial sum to use. Is that error less than 0.005? Yes, it is. The first 3 decimal places are perfect. And the decimal place that follows is off by less than 5 digits. Yeah, actually evaluating this sum without a computer is not going to be pleasant. So there's some neat things that you're going to learn here. This series, the series that we're playing with here, the alternating harmonic series, does converge. But it converges very slowly. If you take away the alternatingness, then you get the regular harmonic series, which diverges. So adding the alternatingness helps it converge faster. In fact, if you look at the statement of the alternating series test, it's kind of shocking. Usually it's pretty hard for a series to converge. Usually it's not enough for the terms to go to 0, right? This is the closest we get to a converse to the test for divergence. So something about being alternating helps series that would otherwise diverge to converge. So you can take a series that diverges and force it to alternate, and the chance of it converging goes up. But series which diverge unless they alternate have a special name. They're called conditionally convergent series. And they usually converge much more slowly, which means that the partial sums take a long time to become good approximations for the full series. If you start with a series that converges more rapidly, then things are easier. So let's do that next. I want to play this same game. We're going to need more practice with this theorem. So let's do the same thing with another series. That's okay. So I want to do the same thing. I want to show that this series converges and then estimate its value accurate with the error 0.005. So estimate S with error less than 0.0005. So the first 2 decimals will be guaranteed correct. The third decimal has a 50% chance of being correct. This is an alternating series. It's 1 minus 1 over 2 factorial plus 1 over 3 factorial minus 1 over 4 factorial, and so on. And I happen to know that this converges to 1 over e, for similar reasons that I know the previous guy converged to log 2. First I run AST. Here Bn is equal to 1 over n factorial. Bn is decreasing. Because n factorial is increasing. And the limit of the Bn's is 0, because it's the limit as n goes to infinity of 1 over n factorial. N factorial goes to infinity really fast. So this is 1 over infinity, which is 0. So the series converges. Now, if I want to approximate that series, if I want to approximate the sum of the series, I use my theorem. By the estimation theorem, S minus Sn will be less than 0.0005, provided Bn plus 1 is less than 0.0005. This is the same as saying 1 over n plus 1 factorial is less than 0.0005, which is the same as saying n plus 1 factorial is greater than, so 0.005, remember, is 1 over 2000. So this is the same as saying n plus 1 factorial is greater than 2000. Now this inequality is not so easy to solve, not by hand, I mean, not algebraically, because there's no nice way to algebraically manipulate the factorial function. But you can check. If capital N is 2, then n plus 1 factorial is 3 factorial is 6. If n is 3, then n plus 1 factorial is 4 factorial is 24. If n is, let's jump to 5, then n plus 1 factorial is 6 factorial. Let's see, what's that? 5 factorial is 120, so this is like 720. If n is 6, then n plus 1 factorial is 7 factorial, which I think should do it, right? What is 7 factorial? Yeah, 5040, which is bigger than 2000. Okay, so the smallest integer n for which this inequality is true the solution to n plus 1 factorial is greater than 2000 is n is greater than 6. In other words, S6 is very, very close to S, and the error is guaranteed less than 0.0005. What is S6? Well, this one's not so bad to calculate by hand. It's the sum from 0 to 6, -1 to the n over n factorial. Again, I will use Wolfram here, but this is 1 over 0 factorial minus 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial minus 1 over 5 factorial plus 1 over 6 factorial. And this guy is 53 over 144, which is 0.368055555 and so on. All right. So I can approximate the full infinite series using the sixth partial sum and be confident that when I do that, the error is less than 0.0005. S6, the sixth partial sum, is the sum from 0 to 6. That's this, which has this decimal expansion. And the full value of S, again, I know this from some work with power series, and I'll show you that after exam 2, is 1 over E. If I compute 1 over E, he has decimal 0.36789, blah, blah, blah. And so just like we said before, the first two decimals are guaranteed to be correct. The third decimal is correct with probability 50%. So our third decimal here is off. But if you rounded this to 3 decimal places, you would get this. So this is a really good approximation for 1 over E. 1 over E is very close to 53 over 144. And what's so important here is that we're able to be quantitative about the error. So every time we've solved a convergence question regarding infinite series in the past, unless the series is telescoping or geometric, we've had no hope at saying what the actual sum of the series is. Now, at least, if the series is telescoping, I can tell you with some confidence what the series is. I can say that this series, S, even if I don't know that it converges to 1 over E, should be really close to 53 over 144. I can say that it's within 0.0005 of 53 over 144, and that's the power of this theorem. So it's the first tool we have for giving the sum of a series besides telescoping and geometric series. AST itself, very easy to use. The estimation theorem requires a little bit of love. Your homework this week, I think I just put one problem in there that uses the estimation theorem, but there are several problems that use alternating series test without asking for an estimate. You need to get comfy with both, and I don't think you'll have a terribly hard time with either as long as you practice it. So I do believe that's about all we have time for today. Yeah, I'm gonna have to cut it here. I've got an office hour, which I'm gonna be switching over to in just a few seconds. So if you wanna talk about more stuff, come see me there. Otherwise, please just continue working. You should be totally done with homework 7, hopefully done with homework 8. If you've got anything left to do with homework 8, you gotta slam through that shit today and at least take a look at homework 9. I want you guys to be working on homework 9 right now. So if you're not up to that point yet, please get there today. If that means that you gotta say fuck off to everything else you gotta do today and just do math, then that's what you gotta do. Because we're in this crunch time for the course right now. That's the way to make it work. I promise if you do that, it will work. So please make the time for this and it will go well. Exam 2 is going to be next Friday. So at our next class this Friday, I will announce the details about exam 2. We will finish section 11.6 and I'll release the study guide so you guys can start prepping for exam 2. Remember, the purpose of the study guide is not just to have you work problems that are of similar difficulty to the test, but also to encourage conversation. So, you know, check out the Discord server or send me some Canvas messages, have a conversation with somebody who knows what they're doing, and make sure that your solutions are making sense, that they're good. Make sure your notation is good. Make sure you remember your theorems. Just keep working hard. And if you have any questions, don't suffer in silence. Please ask. So that is it. That's where I'm going to leave it for today. If you want to talk more, again, come by the office hour. I'll be switching over to that just as soon as I finish going to the bathroom and getting more coffee. All right. I hope you guys have a lovely rest of your afternoon, and I'll see y'all on Friday.